Welcome back to our Chemistry Flipped classroom, and today's lesson is on oxidation reduction reactions, or what we frequently abbreviate as redox reactions. And so we're going to learn this mnemonic today. Leo says GER, and what we're going to learn to do today is understand what an oxidation reduction reaction is, how to identify one, and how to identify what's oxidized and what's reduced. So let's define oxidation and reduction reactions. So in an oxidation reduction reaction, electrons are transferred from one element to another. And many spontaneous redox reactions, well, all spontaneous redox reactions can transfer energy. They may transfer that energy in the form of electrons, meaning electricity, or they may transfer energy in the form of heat, or they may be both. And our non-spontaneous redox reactions can be made to happen with electricity. So transfer of electrons. So if we look at the example of sodium reacting with chlorine, each sodium atom, because here we have pure elements, we have the sodium atom and we have the chlorine molecule. Each sodium atom is going to lose one electron to form the sodium ion, and each chlorine atom is going to gain one electron. And this is where our mnemonic comes in. Losing electrons is oxidation, and gaining electrons is reduction. So you'll notice that sodium is oxidized. It loses electrons. And when we write them like this, we call these half reactions because it's only half of the reaction that's taking place. You'll notice that the oxidation half reaction has an electron as a product. That's because this atom, this sodium atom, is losing an electron. Chlorine is reduced. And so you'll notice that this chlorine molecule is gaining 2 electrons. So we see them on the reactant side. And we have chlorine being reduced. Whoops. So because chlorine here is gaining 2 electrons, and we can't gain 2 electrons if there aren't 2 electrons lost. So we always have to make sure the number of electrons lost and the number of electrons gained is the same. So we're going to multiply this sodium reaction by 2, giving us 2 sodium atoms forming 2 sodium ions and 2 electrons. So we're going to combine those reactions, the 2 sodium atoms forming 2 sodium ions and 2 electrons, with the chlorine gaining 2 electrons to form 2 chloride ions. We're going to put it together, and then you'll notice that we have 2 electrons on the reactant side and 2 electrons on the product side. We're going to simplify by getting rid of both of those. And so we have 2 sodium plus a chlorine molecule yields 2 sodium ions and 2 chloride ions. And we know that those 2 things are then going to be attracted to each other and form the sodium chloride formula unit, or sodium chloride lattice ionic compound. So it's pretty easy to see when we have ionic compounds forming or ions forming. But it's not always this cut and dried. And so we are going to learn how to assign something we call oxidation numbers. And oxidation numbers help us to keep track of what loses electrons and what gains electrons, so we know what is oxidized and what is reduced. So if we look at the example of zinc reacting with hydrogen ions, so zinc reacting with some acid, we get zinc ions and hydrogen gas. And so we're going to take a look at zinc here, and zinc is going to lose electrons. It goes from its elemental state to its ionic state, and its ionic state, it loses 2 electrons. So it's oxidized. And then we have our hydrogen being reduced. It's gaining the electrons that zinc is losing. So each of the hydrogen ions gains an electron, and they combine to form hydrogen gas. So again, pretty easy to see when we're working with ions, but we will learn how to do this with non-ionic compounds, with covalent compounds. So let's go ahead and jump in to how we assign oxidation numbers. So our first rule, this one's nice and easy, is that the oxidation number of any uncombined element is 0. So any element in its elemental form, its oxidation number is 0. And then our second one, pretty easy, is that the oxidation number of a monatomic ion equals its charge. So when we look at sodium and chlorine here, they are both initially in their elemental forms. So they have oxidation numbers of 0. But in the sodium chloride compound, we know now that these are ions. And so this is a monatomic ion, meaning a one atom ion, not a polyatomic. And so it has a charge of +1, which means it has an oxidation number of +1. And the chloride ion has a charge of -1, which means it has an oxidation number of -1. So those two rules are probably the easy rules. The next rule we're going to learn, and we pretty much apply these in order, is that the oxidation number of oxygen in compounds, not all by itself, then it would be 0, but in compounds is -2, with one key exception, and that's when it's in a peroxide, and we'll talk about how to identify those. So in a compound, the oxidation number of oxygen, even in a covalent compound, is -2. And the oxidation number of hydrogen in a compound is +1. Unless it's bonded with a metal, then it's -1. But then it would be an ion. So oxidation number of oxygen in compounds is -2. Oxidation number of hydrogen in compounds is +1. So in water, oxidation number of oxygen is -2. The oxidation number of each hydrogen is +1. The sum of the oxidation numbers in the formula of a compound is 0. So just like when we created ionic compounds and they had to be neutral, we know that the sum of the oxidation numbers is always going to be 0. So we notice that 2 positive ones from the hydrogen plus the -2 from the oxygen gives us 0. And if we were to look at calcium hydroxide, oxygen in a compound is -2. Hydrogen in a compound is +1. We have a total of -1 times 2, which is -2, and calcium is a monatomic ion with an oxidation number of +2. And so this still adds up to 0. So whether it's a covalent compound or an ionic compound, the sum of the oxidation numbers is going to be 0. Last rule. The sum of the oxidation numbers in the formula of a polyatomic ion is equal to its charge. So if we look at the nitrate ion, we're going back to the oxygen rule. We know that oxygen in a compound has an oxidation number of -2. There are 3 of them. So 3 times -2 is -6, and they have to add up to the charge of the polyatomic ion, which is -1. So we know the oxidation number of nitrogen is something plus -6 equals -1. So we know that the oxidation number of nitrogen has to be a +5. We're going to do the same thing with sulfate. Again, we know that oxygen is -2. There are 4 of them, and 4 times -2 plus the oxidation number of sulfur has to equal -2. And so we can see that the oxidation number of sulfur in this compound must be 6. So what you might be recognizing now is that in the polyatomic ions, those 8-ite, hypoite, and per-ate forms are all changing the oxidation state of the element besides oxygen. And that's how they're able to have different numbers of oxygens, but the same charge. Okay, so simplifying these oxidation number rules, I gave you 6 of them. Let's see if we can simplify them and only have 4. The sum of the oxidation numbers in anything is equal to its charge, whether that's a compound or a polyatomic ion. In compounds, hydrogen is +1, oxygen is -2, and we're going to use the monatomic ions, hydrogen and oxygen, to figure anything else out. So here are some practice ones for you. Pick a few of them, do them, and we will go over them in class. As always, if you have any questions, let me know. I look forward to seeing you in class.